Okay, so we'll continue with reinforcement learning today. One of the points is not correct. Course roundup is not correct. But what did we do last time? Because it's a continuation, let me just kind of recap what were the goals last time. Last time's goal was to first understand what is reinforcement learning. Okay, as an extension of what are the base objects. There's of course state and actions. That was the same as before, like context and actions. But now you have a few other things. For example, the model. For example, the transition probability function and the reward function, which kind of capture the model. You also had the value function, and you also had a policy. Okay, the notion of a policy, and policy was also there in contextual bandits, but again we revisited that. So last time the goal was what is reinforcement learning, and second objective was to understand Markov decision process, and we built up in three steps. What is the Markov chain, what is the Markov reward process, and then what's the Markov decision process. Okay, and the third goal last time was to understand what is the policy. Policy is just a mapping from states to actions. Okay, it could be a deterministic policy, which means that in every state there's a fixed if this is a state, do exactly this. Okay, that's a deterministic policy. But there are some policies called stochastic policies where in a given state or whatever feature vector, you can flip a coin. Basically, you have a probability mass function. Think of you have four choices: northwest, east, south. Then with some probability, you'll do each action. Okay, so that's a stochastic policy. The probabilities are determined. Yeah.
So these, as I understand it, these policies are because if you just let your algorithm try to work randomly in order to get a reward,
Yeah.
it may never get there.
No, it may
Policy
with
is
some
sort of
probability
like
with you.
a mid-level function to a function to help it along the way.
No, your algorithm's objective is to generate a policy. So it's like this, right? So if you're thinking of in terms of functions, so you have a problem, which is let's say the maze problem. You are the algorithm. Your objective is to generate a policy pi. Okay, pi is just that function pi, and that's it. Your output is that. If you knew the model of the world, which is in this, you know everything about the maze thing and where the goal is and everything else, you can deterministically compute, as in go offline, figure out some equations, and figure out what the pi is, and give it back to the user. And then the user can apply that policy and do well in life. Okay, so policy is like an output of the algorithm. So if you think in terms of like what is the input output in supervised learning, what's the input? Some training data, right? IID training data, um, features and labels, and then the output is a function which maps between inputs and outputs, right? So the algorithm is what produces that function. Similarly, there's an algorithm here, the RL algorithm, which produces that pi, which is the mapping from state to actions. Okay. And last goal for last time was to understand what is Bellman expectation equation and Bellman optimality equation. Um, we will kind of revisit those two ideas again because I want to restart. I mean, start from where we left off, where we were talking about Q value iteration, and then we'll get to Q learning today. Okay. So the fourth bullet point is something we're going to talk about a little bit more. Um, okay. So, okay, not this one. Okay, it's not very clear what happened. Somehow the resolution. Okay. Okay, so there's a lot of writing here. So let me write down what is a Bellman optimality equation, Bellman expectation equation from scratch in this, let's say from here. Okay. Uh, so Bellman expectation equation just is a recursive relationship. It's just saying what is the so of course so what is these equations are trying to relate. What are the equations for? These equations are for value functions. In this case, let's focus on the state action value function. The other value function is kind of the same. Um, so so what is the state action value function? It's q pi of s comma a. Okay, and this, remember, was by definition is just the reward that you get from being in state A, sorry, in state, I don't know what the notation I used, but let's say RA of S, the reward, immediate reward that you can get, um, plus sum over the probability of going to some state S prime of S8. I think I use slightly different notation, but let's use whatever, the three syllables here, um, times um, what was the, sorry, use the previous slide. Yeah, okay, let me just use V pi for simplicity. So V pi of, actually let me use Q. Q pi at S prime and pi of S prime. So this is, I guess, I should have written it in the center. This is actually the Bellman expectation equation. So let me rewrite it. All it's saying is, what is the value of me being in a state S and taking action A? Okay, that by definition is, oh, if you're going to take an action A, but I already told you a policy pi is basically that, oh, take that action A, you'll get some immediate reward. That was this script R, which is if R is noisy, just take its expectation, and you took that expectation at this state, and you took from because if you took an action A, plus because you took that action A at this state, you will be randomly getting into some other state S prime. With what are the probabilities? So that's the averaging going on here. This is a sum over all the states I can reach, uh, in my state space. Okay, um, the probability with which I'll go to S prime given S comma A. Okay, that's the probability that I'll get to S prime, some a specific state, and in that state, what should I do? You should just be following the policy pi. Okay, if you're following policy pi, I can always use q pi of S prime comma pi of S prime as a stand-in there. I mean, this is actually equal to v pi of S. Okay, by definition. Sorry, S prime. So value of a state is nothing but value of a state action pair where action is determined by the policy pi itself. So both have these pi's, right? So what's the difference between this q pi of S comma A and v pi of S prime there? But in general, let's say here um, v pi of S is that v pi of S is saying, oh, I know in every state what action to take, which is given by pi of S. Okay, so even for the first state S, you have to take pi of S. Q pi of S comma A is saying you don't have to take pi of S immediately. You have a degree of freedom. First action you can take something else, but from moment you reach next state onwards, you have to take according to pi. Okay, so but in Q pi of S comma A, if I tell you, oh, I'm gonna use pi of S for that A first action A, so I'm fixing it, then it is actually v pi of S, right? I mean, there's no difference between those two values. Okay. So anyway, so this is called Bellman expectation equation because it's relating expectation equation because there are a lot of expectations going on. This first term is an expectation over randomness of rewards, if there is any. And of course, this second thing is actually an expectation with respect to what all possible next states I can reach. Okay, that's why it's a sum over probabilities times the next queues at those locations. Okay, at those different states as primes.
So,
Yeah.
is that what causes like kind of the leaking between like states? So, like you can start to see the
This-
reward in a certain direction, like maybe not in a certain direction, but your code can learn that it's beneficial to go through states 2 and 3.
Yeah.
It needs to get to 4 because there's a reward at 4.
Yeah.
So this is kind of what makes 2 and 3 look like an intermediate good idea.
Yes, because queues are the, remember, okay, this was the recursive definition. I'm just relating this to this guy. But in general, there was a straightforward definition, right? V pi of s was all the expectation over all the rewards that you can get, rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 3 and everything, right? Given the starting point is that s. So yeah, so these are value of being in a state and taking action. So if it's valuable to be in some states, as if it's on the path to high reward, then that state will have a high number. So these are just numbers being assigned to, in this case, state and actions. Here it will be just numbers assigned to states. Okay. What I wanted to start with is just saying that this is called an expectation equation because there's bunch of expectations going on, this one and this one. But also it's a Bellman equation because it's relating value at a state action pair to value at some other state action pairs, some other bunch of pairs, right? Because pi of s prime could be some action, go north, whereas here you're currently caring about a value of going, let's say, west or something, right? So this is an equation. This is actually a linear equation. So if you think of this q pi s comma a as some variable x, then you have a x here and you have some other y here. Okay, and those two are related linearly because there's some known numbers. Let's assume they are known numbers. Then it's a system of equations, and you can actually solve them. And so that's so there's no difficulty in figuring out what the q pi of s comma a is if you know the model. Okay, so this is called the model. So this term and this term in general for every state comma action pair, if you know them, it's called the model. So if you know the model, you just have these equations, solve this equation, you'll know the value of the states. If you know this uh, if you know this guy for every pi, if you can evaluate this for every pi, then you can evaluate it for maybe exhaustively figure out for every pi, and then there will be a pi for which these values will be large. Okay, and so that's the pi you want to pick. Okay, so if you're an algorithm, naively what you should do, if you have access to the model, as in these two, okay, as in let's say you have access to a function b. Okay, b is the Bellman expectation equation solver. Okay, so what you do is, you can give it pi of s. Sorry, the policy a policy pi. Let's say you only have 10 policies to figure out what is the best policy. So you start with the first policy, give it to that function. That function will try to solve this equation. It needs that pi because it needs to know what variables should be related to what variables in this equation. Okay. So maybe there are 5 states and 2 actions. So there will be 5 times 2, whatever, 10 equations, 10 unknowns. It will solve it. Okay, it will solve for these 10 numbers and produce it back to you. Okay, so you'll get back 10 numbers for pi 1. Again, for pi 2, you'll get back another 10 numbers. Pi 3, you'll get back another 10 numbers. Okay, you can do that for your 10 policies. And then it will turn out that there will be one policy which will dominate all of them across all 10 numbers. Okay, it will be like some sort of a dominance, and that policy is the best policy. Okay, so that's the offline problem. There's no reinforcement learning here because the model is known through this function. The function is not directly telling you, but the function had access to this number, so it will produce these value function values. Okay, could tell you the values. So that's one naive way to understand how an algorithm can produce the best policy. Okay. Um, but we'll do that while learning, and that's so. There's one more equation that I want to kind of flash, which is Bellman optimality equation. Okay. So Bellman optimality equation is saying there's going to be, as I said, we care about. Let's say we have rewards situation, so max over pi of q pi. Okay, of s comma a is what we care about. Okay, so given s comma a. Okay, so given so we want to find this, and this max, okay, is this R max, or the policy which maximizes these cube state action value function. That's the optimal policy, and there is a corresponding the values themselves. They satisfy an optimality equation. Okay, And the equation is also pretty intuitive. It's basically, let's call it q star of s comma a. Okay, so at a given state and action pair, let's call the best value that any policy could have had. Let's say there's a best policy. You just don't know it. Okay, if you executed that policy, if you always follow that policy, then q star of s comma is just saying what is the value that you can get in the current state if you take an action A and then follow that best policy, right? So because it's the best policy, you hopefully your values are high, except modulo the first choice of action, which is all anyway being captured. So this um, is equal to again r of s comma a plus sum over s prime of p of s prime given s comma a times, again now there's going to be a max over a prime of q star of s prime comma a prime. Okay. So this is called a Bellman optimality equation. And the intuition is from dynamic programming. I think I very quickly mentioned it last time, but it's basically so dynamic programming has two interesting properties. I think one is the problem substructure property. Um, what is the other one? Okay, I don't know the optimality principle. I don't remember the details, but let's understand at the definition level. So basically, what we want to say is that if you knew what's the best, if you knew q star at a future state, okay, so you are at state s, okay, from s these are all the possible states you can go to s primes based on whatever action you take, right? I mean, in this case, if we take action A, these are all the possible states you can go to. At those states you already know what's the best value you can get. Okay. I'm not telling you the policy, but there is a policy, and corresponding there is a value at those new states. Okay, and so of course, if there's a value at this new state by taking different the best value that I can get by taking different actions, I'm going to take the action which is the highest, which is the highest value. So that's why there's a max operation here. It's just saying I was at S, I jumped to S prime. At S prime, there are so many options that I can pick. Of course, I'm going to pick the one which is the highest. Okay, right? Pick the one that's the highest, and then because I picked the one that's the highest, plus uh, the immediate reward I can get is basically the best value I can get now. Okay, for this given state and a given action that I'm going to take. Okay, so these two are fixed. I mean, I'm already in state S, and I'm saying, oh, I want to take A now. What's the best thing I can do? I mean, this guy is going to be fixed. Okay? Because you're in state S and you took action A, you'll always get this reward in expectation. Okay, but from here onwards, because there's a Q star guy at S primes as well, so there's going to be at every different S prime, there's different Q star functions. You're gonna at any state that you land, you're always going to pick the best action there as well. Okay. So that's the Bellman optimality equation. This is a substructure. Okay, it's like saying the shortest path you want to find um, from some source to some destination. If you already have the shortest path up to one hop, you know. So basically, like this, right? So if you so if this is a destination, this is a source, and maybe this is the shortest path. Let's okay. Right, so so this relation sorry, this equation is trying to say that uh, if you already know shortest path from here onwards for any one hop neighbor of this guy, so maybe there are three neighbors of this guy. For each of the neighbors, you already know the shortest path to this person. I mean, the destination. Then of course you're going to pick the part which is the shortest in this case. So it's not the max but the min. But pick the shortest, and then hopefully you'll pick the shortest jump to that. I mean, it's once you pick this, and this is kind of fixed. Okay. So it's like a substructure which is being exploited. Yeah. Oh, so the other property I was talking about with dynamic programming is like the substructure property and the repeated solving of these subproblems. Okay. So there is some efficiency gain going on, but let's not worry about it. For us, just understand that there is some uh, intuition of why this equation makes sense. Okay, this is called the optimality principle. Yeah.
In that equation, max of q star is coming, right? That will also depend on corresponding reward.
Yes. Yes. Yeah. It's a recursive equation. So these are recursive equations. Yeah. It's just we have not solved the problem. Okay, these equations are just characterizing what these. So ideally, we are supposed to solve this problem, right? So this the one in the bracket. Okay, if I can, if I in the previous slide I told you I can find q pi of s comma a for any pi because I have this be function. Give me any pi, I'll produce q pi of s comma a. Then you know how to solve it, right? So you can solve the star problem by saying, oh, plug in every pi, produce the q values, and pick the one which has the highest value, right? But here we are saying this is just a characterization of the solution, that whatever is the solution of this problem, star problem, let's call this solution as q star. I mean, the solution is pi star, but the value of that problem, the objective value, is called q star. Okay, so there's a difference between the solution of the problem and the value of that solution. Okay, if you plug in pi star, there's going to be corresponding q, right? So that's called q star. So, but q star satisfies this equation is a claim. Okay, it's like a characterization of the solution, or, or the solution satisfies this property. So either you can solve some sort of an optimization problem, or you can say, oh, can I solve this problem by itself? This is a system of nonlinear equations. Okay, unlike the Bellman expectation equation, there's a system where this is unknown. Let's call it x. This is also is unknown for every s prime. Let's call it y or z or whatever number of unknowns there are here. But they are related to each other through a nonlinear operation, a max, right? It's like saying x is equal to some 10 plus zero point 0.3 times max of y comma z plus zero point 0.7 times max of z comma w or something. So this is the relation between x, y, and z and w. So this type of equations, this is one equation, and you can know, like, if you have 5 states and 10 two actions, then you'll have 10 such equations. So it's not easy to solve this style of equations. Okay, but it's a bunch of equations, you can solve it. So that is the equivalent effort of solving this guy, if you have that, like, let's say you have oracle or something. I don't know. Any other question? Yeah.
So the Bellman expectation equation is just a general representation of finding out q pi, while the optimality, the Bellman optimization equation is where we're trying to find the best possible q pi. Right?
Yeah, optimality equation is the characterization, the optimal solution of this optimization problem. So optimality is a non-triviality here. Bellman expectation equation was by definition, right? So we saw, it's like saying, okay, q pi of s comma a, by definition is apply, s comma a plus, right? Take something right now, and then it was basically um, expectation, or it's basically rt plus 2. I mean, there's a gamma here. Actually, there's a gamma missing, I think, in the previous slide as well. Plus gamma square rt plus 3 plus, and all these guys. Okay, so there is this, remember by definition the value is this. Okay, value function. So maybe the expectation like this. Okay, expectation is just to pi. Now that expectation equation we got by just observing that this by taking gamma out, by looking at this, since this is still an infinite summation, infinite summation, this is nothing but gamma times sum over s prime, if you want to actually capture like this, s comma a of q pi of s comma pi of, sorry, s prime. Yeah, something like this. That's all. I think we've seen that in one of the slides. Okay. So expectation equation is, you don't even need a Markov addition process or anything going on. We saw that for even Markov reward process. Okay. Um, right? I mean, I can actually go back to that slide if you want. Just to Markov chain, Markov rewards. Yeah. So this is for the just the state value function. We saw, okay, state value function is expectation of return, total return. Total return is this huge summation here. The huge summation you can take a gamma common, and there's still a huge summation, and so you gamma common, and then you have this return at t plus one time instant, and return at t plus one time instant is this value. Okay. So the last but one step to the last step, there is an expectation being pushed inwards. Okay, expectation from time step t plus one onwards is being pushed inside. That's why you get a v there. Okay, from g to this guy. Okay, so this is the same trick for Bellman expectation equation. So that's there should not be any wonder there. Bellman optimality equation is something which needs to be reasoned properly. Okay. So So what I want to so let me restart at this point, which is so what is this point? Um, as if like we've talked about MDPs and we've talked about what is the state, what is the action, what's the state action value function. So the Q stuff that we saw for the past 5-10 minutes. Now I'm gonna try to talk about Q learning algorithm. Okay, so we'll restart from this point. So I said in general. So Q learning algorithm, what it's going to do is it's going to produce a policy at the end of the day. Okay, so all these algorithms, as I said, they have to. There's a Q learning involved, which means that there is no model. In the sense, it has to ask a simulator or actually do something in real world and figure out what's the reward. Okay, at the end of the day, after a lot of interactions with the real world, a lot of interactions with some simulator or something, at the end of the day, it's going to produce a policy. Okay, what is the policy? It's background from state to actions, and then hopefully that policy is really good. Okay, so that's the goal. And to get to a really good policy, first you need to understand uh, how good a given policy is. Okay, so even if somebody gives you some policy, you should be able to say how good that policy is. Okay, so that's called a prediction part, and there's a control part which is to improve policies. Okay, um, okay, so first we start with the idea that let's say you had access to the model. Okay, so although Q learning, at the end of the section, we are going to not have access to the model, as in we don't know the P, script P and script R. Let's assume we have script P and script R. Then this is literally what the Bellman expectation equation looks like to understand the value of a policy. So if I tell you pi, can you tell me v of pi? Okay, so that's what a value. That's what evaluating a policy means. Okay. So v of pi, you can just do that by relating value at a given state with values at one states, all the reachable states. And this is like a dynamic programming style thing, which is just saying take the expectation of all the next states that you can reach. Okay, these are the four states you can reach. Then it's the average of all those four values at all the four states. Okay, so that's like valuing this policy pi. And yeah, let's not focus on this. Let's ignore this for now. Now that was when you had the model. If you did not have the model, what would you do? How would you value a policy? Okay, you still do something simple, right? Which is that uh, if you didn't have the model, then you have to have at least a sample. Okay, what is a sample? It's like either interact with the world to get a sample of, oh, if I do this action in this state, I'll get to that state. Okay, so that's what I mean by sample. So you need to at least have state, action, next state, data, and reward, hopefully. Okay, so that's one sample. Okay, so if you did not have the model, if you can generate the sample either through interacting with the real world or through simulator, then you're still good. Okay, then what you can do is get that sample. So you get those numbers. So you're in the state, take some action, get some get immediate reward, and get to some next state. Okay. Now using these four numbers, you can still kind of approximate um, the thing which is circled above. So in so I'm giving I'm switching between state action values and generally state values, but it's the same idea. Okay, there's no big difference between them. So okay, let me do it cleanly. So q pi of s comma a is r of s comma a plus sum over times right. Now, as I said, we don't have this model, as in we don't have this part. So instead of the underline parts were not there, double underline. Okay. So what we're going to do is we're going to say, oh, if we don't have it, then there is some reward that we collect. Okay. At, let's say we are at time step t, and we are in state s. We took some action. We got some immediate reward. Okay. And we reached a particular state. Okay. So maybe that state is S prime. Then in that state S prime, okay, actually there's always a gamma missing here. So gamma times q pi of S prime and then pi of S prime. Okay. So since I didn't have this expectation, I got the actual sum reward specific to realization. I didn't have this model instead of summation. I actually landed in some state S prime, and so there is no this summation as well. There's some state S prime, and this would be my approximation for this right hand side. Okay. Now, what will I do? Okay, if that's an approximation, the intuition for an algorithm is to for just evaluation to find out how good a policy is. Okay, is to start with. You may have a conception of how a policy is. So maybe I had some q uh, pi old at this s comma a pair. So I had at this s comma a pair, I had some previous value of what the value is. I got a sample. Okay, this is a sample. Then I'm going to take some sort of an average between these two, some new data and some old data. So I don't want to forget what was my, let's say I had a really good high quality estimate of how good the value of that state comma action pair is, then this additional information may not be useful, right? So I have to balance new information and old information. So I'll just think of it as maintaining a running average. Okay, in the sense of I had some previous estimate of how good the value is. I got some one sample data at the same state action pair. I just need to add it to my average to get a better estimate of the same q pi of s comma a. Okay. So all I'm saying is, let's call this q pi new of s comma a is an average. Let's say alpha times this plus 1 minus alpha times that. Okay, where alpha is, let's say, zero point 0.1 or something. So it's like zero point 0.1 times some new information plus zero point 0.9 times old information. It's fine, right? It's like a running average where we are retaining what we knew before plus some new information, taking an average between those two. Okay.
How old will be the previous stage?
Maybe at the so maybe let's think of so far for the next maybe sometime 20 minutes or so. We'll think of tabular situations. So think of this thing as a table. Okay, I have a bunch of numbers already. As I said, if I have 5 state and 2 actions, then only 10 numbers I need to keep. So think of that as a table. Okay. And these 10 numbers I had previously, but now I got a sample, which is I was in some one of these states, maybe the second state, and took the first action. I got to some other state, and I can find this number. Right, this is a proxy for getting that full number. Okay, so let me just put here old as well. Okay, so all I'm saying is you have this table, okay, which is, let's say, 5 cross 2. Just means there are 5 states and 2 actions. So let's say we are in the state 2, Okay, and we took the first action. We are in this cross. Okay, this guy. Okay, and we want to we were in this state and took some action, and we landed in some other state S prime, and got some reward RT plus 1. Okay, so RT plus 1, I have new information now. I know that I landed in new state S prime. That is also new information for me. So I want to update some number here. Maybe the value I previously was 10. Now I want to change it to something else. Okay. I'm just saying, oh, whatever the value, multiplied by zero point 0.9 and multiply with zero point 0.1, whatever some new value estimate that you're going to make. Okay. This is the value estimate because remember, this is just a proxy for this guy. And this guy is supposed to be the same as q pi of s comma a. Okay. It's like I'm making from the Bellman expectation equation. I'm making an iterative algorithm. Okay.
So during the training, we also want the alpha one.
No, fix the alpha to be something. Yeah. Um,
And during the alpha screen is determining what percentage
how
of
to average? Yeah.
what percentage of the new information you take and what percentage of the old.
Yeah. Yeah.
Maybe what R is a symbol R T plus one and gamma.
Yeah. This is like a realization of. I mean, so I use t plus 1, but just ignore the t because there is no time index anywhere. So it's little r is like an actual realization of the reward that I got. Gamma is the usual discount factor, which is like zero point 0.9 or something.
And that was the symbol or
The gamma is known beforehand. Everybody knows gamma fixed. R is something that you got. So what did you get? What is the sample? What is that particular trajectory? I mean, or what people mean here, from what changed from this picture to the next picture, is a specific reward you got and a specific next state you got. Okay. So um, yeah, and what is this diagram here? The white circles are showing states. The black dots are showing actions, and green squares are showing end of the trajectory. As in, like if you take that action, you die, for example, here, or reach the goal or something, whatever it is.
so getting back to what the
Here, yeah,
so this is like where you have these
yeah,
this is basically after that we took some action.
yeah. So we are already in S comma A in this state.
We jump to
We take an we know what action to take. Okay, so we already said S and A. So the only thing we get is a next a reward and jump to a next state. I'm just calling it S prime. It could be S2, S3, whatever it called. Want to call it. Yeah. These are the two new information that's revealed. That's all.
so let's say according to that we have five total states.
Yeah, we have five. So that's, let's say the S prime is like state 3.
Yeah.
Okay.
We can jump to like any state between these five, right?
No, no. I mean, so here S prime realized to be 3. Then you just have to use the number at 3, and then whatever the pi was telling you, whatever the action was, that corresponds to a number, right? Either this number or this number. Just use that number here. Gamma is known, this is known, so this whole thing is a number. Just use that number to update the cross. So the whole objective is just to update the cross. Because I'm in state S, and I know I took an action A, okay, I care about just knowing the value of being in state S and taking action A for this given policy pi. Pi is fixed. Okay. So here I'm just trying to learn pi is always fixed. I want to converge to a bunch of good numbers here, and the numbers are supposed to be so. Here, so I think I may be confusing you guys a little bit. So let me do a take two. Okay, what are we trying to do? Okay, so Bellman expectation equation was saying q pi of s comma a is sum r of s comma a plus sum over s prime p of s prime s comma a of q pi of s prime of pi of s prime, right? This I said was a linear equation. Linear equation. Okay, linear equation in a sense is something like example x is equal to some zero point 0.3 plus 0.3 times y. Okay, no, I don't even need brackets. 0.3 times y plus zero point 0.7 times z or something. Okay, some equation like this. It's linear equation. Okay, what is what? So other thing is like there are only two next states to go to s prime is two. So each state you don't know anyway the q, so that's why I'm. So by getting such linear equations for every state action pairs, which would be if there are 5 states and 2 actions, there'll be 10 such equations. Solve it, you'll get the q pi's of s comma a. But there's another way to solve this. Okay, so that's what I think I was didn't connect it properly to you guys. Second way is to solve it is to say, oh, I want to find q pi of s comma a. The way I'm going to do it is in an iterative fashion. Okay. Okay. So this is a system of equations, right? Which means that this x, y, z are unknowns are I'll basically call the fixed point of this equations system of equations. Okay. Fixed point just means things which solve that equation or satisfy that equation. I can do it iteratively where I say, okay, q pi of s comma a is gonna be r of s comma a plus the same thing s prime p s prime s comma a q pi old of s prime comma y of s prime q pi new. So I'm going to do it iteratively where I'll say, oh, start with some arbitrary numbers. Apply, I mean, you know these numbers, let's say. Okay. Do this transformation, you'll get some new numbers.
That's the actual reward. So that should be small r.
No, yeah, let it be capital R in the sense that you know the model in this case, let's say. The previous slide was saying if you don't know the model, now let it be small r and let there not be summation. Okay, I jumped one step. All I'm saying is to solve this equation, you can either it's a system of equations, you can solve it directly, or you can do it iteratively where you say, oh, let me fix the right hand side, start with some old numbers. Because I know the old numbers on the right hand side, I can compute the left hand side. Now let's call the left hand side the new old. Again, compute the right hand side, call them the left hand side, and repeat. Okay. So you can do this iteratively. Not it doesn't work all the time, but there's some nice thing about because these are probabilities, and there's something nice about the structure that it's called a contraction mapping or something. Anyway, so that this things. So if you do it iteratively like this, you'll still get the same answer as solving the system equations directly. Okay. So whether you solve it using, you know, whatever Gaussian elimination or something like that here, or you do it iteratively here, you get the same answer. Now, what I was talking about in the previous slide is just, oh, what if we don't have models? Okay, the summation is not there. Then if I'm at s comma a, okay, so I'll still have these old values, okay. But if I has some, but if I have at s comma a, I want to update to the new value, okay. I'll use the old value plus some specific realization little r plus the q pi for a specific state that I went to, okay, because I don't have the model. That's all.
So every time when you are training, you are basically kind of learning the probabilities also. Because
Every time, wait. What is it?
so basically, what I'm not able to understand is how do you get these probabilities of jumping into the next step?
These properties, these are not there. Okay, what we have at any given state and action is, if I take a specific action, the exact next state I'll get to, and what is the reward I will
It
get.
is very deterministic that there will be only one state where
No, I may get to some other state. If I take the same state, same action, I may get to some other state as well. That's why there's stochasticity, right?
yeah. So we have
But right now our trace, our data. So for us to update, for example, if you see the previous page, for us to update, we were just saying that, oh, if I'm in state S and I took this action, in this particular case, it happened that this is the reward that I got. Maybe it's zero, maybe it's some number. Plus that I know that I went in this particular case I went to S prime. So this is how I'm gonna update.
the
Okay.
probability.
Update the Q values. I don't care about learning the probabilities. So I'm not really learning the probabilities and rewards themselves. Okay, that's not the learning problem. Here the learning problem is to just figure out what is the quality of a given pi. So because ultimately my algorithm is supposed to produce a high quality policy pi, right? I don't care about the model of the environment. I don't want to learn the model of the environment itself. Okay. Yeah.
So from what I understood, you had some notion of what your Q should be
Yeah.
because you did not know your reward. Then you perform an action, you actually find your reward, then you realize that you need to keep updating your Q. So
Yes.
to get to Q final, you ideally want to visit every single other state, know the reward in every situation, that will give you the Q new final, because then you know the reward for every single state. So you jump from state 2 in your matrix, you jump from state 2 to another state, you got your reward,
Yeah.
and that's how you update Q.
Yeah.
So you ideally want to go from this state to every other state. Am I understanding this correctly? Where if you
That
know,
part is not clear to me.
Every state and every sample.
yeah. So in your 5 into 2 matrix,
Yeah. So for this case, I'm saying if you are in second state and first action, you have somehow jump to third state and some action.
right, and then you found out R, and so you got Q new.
Yeah, I got new. I computed this, and now I'm done. Now it's a fresh start again,
Okay.
and I mean now some new state S prime, which could be let's say third row. Now I want to compute the value of both, being in, taking action one or action two. Again, I'll sample. I'll take action one, figure out what happened, which is I again got some other reward and some other state, and I'm going to use that to update that cell. So I can do it sequentially. Yeah, yeah. I don't know how many of you, some people have lost on this side. Yeah.
I've lost the thread a little bit, but you're assuming that you know the reward in advance for every state.
No, we don't know this. So this is what is the so I think I had some pictures, right? So at the very beginning there was this example with which outlines how the interaction goes. This is how the interaction goes. So I know what state and action, what state and what the previous reward was. Okay, I take some action. That's what I send it to a function or something environment. That tells me, gives me back the next state and the reward. Okay, these are the two numbers we use in that equation. The little r that I was writing is like rt plus one.
And the function being the policy.
No,
So
I
you
guess
said
I
the
guess
function-
responded this. Okay. What do you mean function?
You said that you send the state and the reward into a function.
No. I just give the. I take an action in the environment. That's what I need to do. Right?
Okay.
So that's taking an action in an environment is as good as saying I apply this function, give it as an input to. So apply this action. So give this action as an input to a function.
Okay.
See, action is the input to a function, and out comes the next state and the reward. It's like a state machine for the environment where you give an action, it will say, oh, because you told me to take this action, this is the new state, and this is the reward you get. Yeah.
Okay. And but how would you know, for example, in a game you made a move? What's the reward? You have.
Yeah, you would get zero
You
reward.
just made
Yeah.
zero.
Yeah.
So essentially, all the rewards, there's going to be thousands and millions of zeros.
In a game, but
In
not in other settings, huh?
In a complicated game, there's going to be millions of zeros.
In a game, yeah. In a game, but not in general. This is like beyond games, right? But yeah, in games it could be zero, but in Atari games it's not the case. In Atari you'll see the delta in the score as you, like if you have played Breakout, like actually there's a video right here, right? So you can see the score increasing here. That's the immediate reward. Like 3, like instead of, I don't know, 3 minus 2, I think, like 4 minus 3 is the delta, is the immediate reward.
And does the state include all the information known at that point in the game?
Yeah. It's some function of everything that has happened so far. It could be some summary statistic. Okay. In this case, the summary in this we will get to soon. Is state is just a screenshot of this game. The computer is, or in this case, the algorithm is just seeing a frame as in a picture of this screen, just like humans do.
Okay.
Okay.
So
Not one
all-
picture, maybe 4 frames, but that's
And
nuance.
so all the moves they make until there's a score, the reward is going to be zero. After there's a score, there'll be a reward of 1, for example, in this game.
The move is just moving the paddle. So every time they move the paddle, they know exactly what the score change happened.
Well, but there's, I think the point he's getting at in this particular example, the ball is traveling on the way up, so there's a delay in the reward.
Yeah.
So,
So that those rounds is zero. Yeah.
yes.
So I think we know the value we'll get to based on certain action. But the value of the reward we'll get, initially they're all zero. But for example,
There is no value of rewards, but like there's a value for a policy. So if this paddle is following a fixed policy, we have been just discussing what is the value of being in this state and the paddle being left or right or whatever, right? So we are just figuring out the properties of a policy. In this case, the fixed policy, then all the possible states and action pairs. What's the number? What's the is the good state action pair to be in, or is the bad state action pair to be in? Okay. And to do that is what we just saw. Yeah.
During the training time, we are just learning, finding the optimal policy.
We haven't talked about training time, test time, and anything like that here.
When we start this, like what we're not able to understand is how this data comes into the algorithm.
Yes, so that's precisely that's what I was saying, right? So is it? So we'll get to, so as I said, the starting point for us to understand how to talk about Q learning, right? So now it's a learning algorithm. Learning part just means I don't know the model, okay? But the algorithm's input is still, input is nothing. For example, this algorithm, it knows what this, so input is basically what is the states, what is the actions, okay? If you really think of it that way. It doesn't know, and it just needs to figure out what is the best mapping from states to actions, okay? The algorithm has to produce pi, okay? But the algorithm doesn't have access to the model. If the algorithm knew states, actions, but also rewards and script R and script P, then as I said, it's basically an optimization problem. And we saw I wrote the optimization problem a couple of times. Maybe actually let me flash it. Um, the star thing. Okay, if I tell you what the although it's here, I'm not saying it. But if I tell you the model, then this problem is some sort of an offline optimization problem. Okay, it can be solved using what is called dynamic programming or variations of dynamic programming. Okay, but Q learning does that when you don't know the model. Okay, and to do that, we are figuring out how to manipulate these Bellman expectation equations and then get to optimality equation and figure out how to learn. Okay, so what is Q learning going to do? It's ultimately going to again figure out some Q values. Okay, Q values as in state action value functions. But once it learns, as in figures out good Q values, they literally encode what is the best policy. Okay, I'll probably discuss that right now. So if you know, in fact, where is it? Q star. Yeah. So here Bellman optimality equation. This, if you know Q star, then the best policy is just argmax. I mean, I think that is obvious from there. Argmax of Q star of S comma A over A is pi star of S. Okay. In a given state S, what's the best? What action to take is take that action which is the highest, which gives the highest Q value among, let's say, two choices that you have. So if you know, so the Q learning is going to learn this guy, okay? And if you learn this guy, then you know what the best policy is, okay? So that's what the learning. So, but to learn this, if you know the model, you can learn this easily, okay? As I said, this is a system of equations, not system of nonlinear equations in this case, like this. But if you can solve it, then you know what x, y, z are, which is literally Q stars, and so you can figure out what the solution is. If you know the model, if you know this capital R and these, but we don't in reality, okay? And so we'll do the Q learning way of doing it, okay? Is that a little bit clear? Who's not completely? Who has some other questions? No.
I doubt any of us are.
Who's completely lost? Is what I was gonna ask. Okay, so no, it's fine. I think it's a good point to ask questions, because okay, I think those two slides were a little bit confusing. Let me start here. Okay, so the first point is what I kind of alluded to: how to turn a Bellman expectation equation, or actually you can also turn the Bellman optimality equation into an iteration. Basically, right hand side, start with some random numbers, evaluate the right hand side, think of that as the new numbers, again apply those numbers into the right hand side, again evaluate the right hand side, and so on. So except that the Bellman optimality equation, the right hand side is a max operation, Bellman expectation equation doesn't. Okay, but it turns out that if you can do this iterative update, okay, you can actually get to Q star, because those the equations have some nice structure. Okay, so there's some contraction property happening. Okay, Contraction property just means that if you start with two different um, what is it, value functions, then you get them, they become closer to each other once you apply this right hand side operation, whatever you do it. Okay, but anyway, so this iterative update part is just saying instead of equality, so the iterative update part is basically something to do with this equality. Okay, so this was the equality Bellman optimality equation, right? Q star plus comma a is the immediate reward plus gamma times this plus max. Uh, yeah, this max. Okay. So iterative update was just saying, oh, start with old values, update to new values, old values, and do it. Okay. Now the second thing is, so this, by just doing that step, that change itself is called value iteration. Okay. So with that change, what we still retain was the model, because the model is still here. So it assumes that if you know the model, if you do this iterative change, then that style of algorithm to solve for the best policy, if you know the model, which is that offline problem, is called value iteration. Okay, and in this case, it will be called Q value iteration because there's Q functions involved. But what we'll do is do another change, which is what I was writing, is that we don't have access to the model, so we'll just use a sample. Instead of this capital R, we'll actually use the little r that we actually see, because in that state we took a specific action. The little r that we saw, and the little s that we actually went to, that's the only one we'll use. Okay, so there will be no summation, there will be a specific little s that we'll get to, and just use that little s as the first argument. The second argument, you'll just use the old values, whichever is the max, same thing. Okay. There will be old Q values, right? Remember that the 5x2 table example that we had. There will be old Q values, and so you're just looking at which was the state I landed in and take the max. That's all. And that's written in some details here.
Why would you take the max at that time? Because there are old values you already know for every action there is a value,
Yeah.
but you are not, you have to compare it with any other. So it would
No,
be
this was the original Bellman optimality equation. Now we care about optimizing, not finding the value, not finding the value function corresponding to pi. So there's no specific pi specific evaluation of value functions going on. So there are several ways to think about how Q learning comes in. So far, I think what I was trying to write here, like here, not here, but these slides are these are Q pi's. Okay, Q pi, and maybe even here, it's something to do with Q pi. Okay, just evaluating for a given pi, what is the values? But I have in the so that's also okay. That's also an important question. Okay. Um, but here we're directly trying to solve for Q star of S combined eventually. Okay. So if you know the model, you can just do it iteratively. That's called value iteration. If you don't know the model, plug in the numbers, plug in specific sample numbers, and just do the same thing iteratively, and that's Q learning. With one more thing that you are supposed to do, which is exploration. Okay, which is not present. So this equation is saying, oh, in the state S, what is the action that I'm supposed to take? So for example, let's say you started with in a state S and you took an action A. You went to some state S prime, so you did use that equation, okay? But you are now in new state S prime. What action would you take? Okay. So what action you would take is, because you have current Q values, you either be greedy with respect to the current Q values, as in like assume that this is the best guys and take the action corresponding to the Q values, or with small probability take a random action. Okay. So that's like the epsilon greedy step that you saw in the 2 lectures ago in bandits. Okay, so why are you doing that is because and it kind of is very critical here is because all the estimation that we're doing of Q stars, for example, it's all dependent on it's all dependent across time. It's not IID data. The fact that you reach this state S is not independent of all the things that happened before, as well as the numbers that you have kind of stored for each of the Q stars. That's not independent of what all has happened before. Okay, and so the sequence of kind of policies that you use, they might not have touched some other part of the state space, or some other might have completely ignored some actions completely. So you don't know if they have not tried something. You don't know whether they are a good choice or not. Okay, so there is that exploration exploitation issue. Uh, so let actually, if you look at the algorithm, you will see that it's very simple. This pictures are probably um, I think I'll skip that. Okay. So here is the Q-learning algorithms equation. Okay. It combines the three ideas. Okay. First idea is the equality. Okay. Remember there was this Bellman optimal equation, the equality, drop the equality. That's the first idea. Second idea is averaging. Okay. Averaging. So it's basically, so this averaging may look suspicious to you guys or not clear to you guys, but it's basically alpha times a new number plus 1 minus alpha, right? 1 minus alpha times the old number. Okay? Because there's a 1 in the front here, 1 minus alpha times the old number plus alpha times the new number. Okay. So that's the second idea. And third idea is clearly you don't have the model, so you get a sample. This R and S prime is just one sample. Okay. That's it.
So your max of Q, that Q is the old Q, and even the previous equation, wherever max of Q is, that's the
Yeah,
old Q.
yeah. Whenever you don't have, yeah. I mean, if you don't, whatever information you have currently is what you use. You can't like, yeah. So wherever anything on the left side, you have to use the old Q values. And this is the update. This is a new Q value. So I could have called new here and old here. But since this whole equation, if you get one sample, so in the state S, I took an action A, I went to new state S prime, and I got a reward R. Okay, that's just one sample, let's say 4 tuple thing. Then I can update only one entry in my table, the 5 cross 2 table, right? Well, with one entry update, now you have the new Q, Q or whatever, Q matrix. And then again, at that S prime, I can take an action either greedily or with randomly, and then given an action, again I get a new reward and a new next state, and just keep applying this. That's Q learning, and I'll kind of show this algorithm in a slide again.
So this is basically when we are doing this last thing,
Yeah,
like let's say we are changing state S prime,
yeah.
and really we try different actions right from there and see.
No, what you don't have to do anything at this point. So at this point, you are in state S. You took an action A. There are only two new things that got revealed: new state and immediate reward. That's it. With this information, now you're going back into the drawing board and figuring out what is the updated table. Update the table. Now you go back to reality. Now you are in that new state. Now you want to figure out what is the action to take. That I'm saying, be greedy with respect to the table, or be take a random action.
So what exactly is the again the max function going over?
What is it?
Sure, there are two. If there are two numbers, right? There are two actions to take. Think of the 5 cross 2 example. Two actions to take
From the state S prime.
at this S prime. Yeah, S prime is fixed. The two actions take. It's just saying pick the highest number. That's all.
So within a sample between pair values, take the max.
There's no, yeah. I mean, the only sample from the sample you're just getting the index of the new state. I mean, the new state. That's all. These numbers are there from before. It's just the max of the two numbers, for example.
But to know which one is the max,
Yeah.
you would have to go to that state and then do another sample.
No,
Then it
no. You have the
reveals
old
the
numbers. You have the old numbers. So the way, let me do that 5 cross 2 example again. I mean, I didn't do it very cleanly anyway before. So let's say this was some 10 units, okay? And this is state 2. And the new state is state 3. Okay, so S prime is state 3 and S is state 2. And you are in action A1 and A2. Okay, so let's say A is equal to A1. Okay, so the question is, these are the old numbers. So this is 10, this is 10. Okay, do you guys agree? This is an old number because that's the entry 10, this 5 cross 2 matrix. So at this state, at this action, this is 10. The same state action, this is 10. This is two terms are the same anyway. You just want to figure out what is the 10 going to update to. Okay? Now, maybe you saw an immediate reward of 1 or something. Okay, so then that's going to be 1. Okay, and then you went to state 3. At state 3, this was maybe 5 and 15. Okay, some two numbers that you already know from before. So you always kind of have a table from before. You kind of only update with each sample. You kind of update one entry in the table.
How do you have those values from before?
Start with random numbers if you want. Okay, it's an iterative algorithm. You have to start with something and then converge to some good
So
numbers.
5 and 15 were random, like, as of now.
It could be learned from before or whatever. Yeah, at this point,
Yeah.
it's already there. I don't know from where we got it. We are in somewhere in between. Okay? If you're at the beginning of time, yeah, all these useless numbers. You can set them to 0 if you want.
So the easier example could be like if it's like digital ad clicking, like click or not. If you know you take this action there and click on it, you want or zero. So like it's learned, right?
Yeah. All these numbers are being learned. These are the values of uh, being in some state and taking some action. You can. You start with 0, okay? They will get updated for sure.
Let's say the reward is not decreasing or something.
What?
So let's say the reward
Yeah.
we get
Yeah.
jumping into the next stage.
Yeah.
Like you showed that game,
Yeah.
you had all the negative rewards, and
Yeah.
at the end, the negative reward was kind of you were going towards the positive.
Sure.
So even having all the rewards 0, then why would
These are not rewards. These are not just rewards. These are the estimates of the cost to go. The total cost to go. Okay. These are not Q values are not Q values are value functions. Okay. These are like total. This is like the total reward you can collect from this state, taking this action till the termination. So they are not immediate rewards.
even in the value term also, if
Yeah.
if going to the final state,
Yeah.
remaining in my own state, I'm at let's say value 0.
Let's say these are 0. Sure. What is the issue?
So if,
Let's say this is 0, and you use 0 here.
so if
You updated your number.
So I'm saying that, like initially when you said in that game thing,
Yeah.
that you have to kind of reduce your, and go towards the positive thing.
No, that will come out as a, there we had a fixed policy. There was some particular direction, go north, go east, and so on. Given that policy, we said this is the values which is the value of that policy. I mean, the values we just computed by saying, oh, every time we are not near the goal, it's -1. So the moment you're further and further away from the goal, it's -1, -2, -3, -4, whatever. Sure, but that's the number, right? That's the value of being in that state. So the further, so you being in some state further away from the goal is the kind of very negative. Yeah.
We are saying we can start off with any set of numbers.
Here we are learning. So there it's given. -1 is given, so you're just adding those things up. Yeah, here you can start with any numbers. I mean, of course, the numbers will influence how well your algorithm runs because here we are learning. Okay, so if the numbers, of course, are close to the ground truth, as in close to the optimal numbers, then you're immediately learned. Okay, and if they're not, then you will take some time. But you can start with any bunch of numbers. Actually, that is a little bit imprecise as well, but let's move forward. So, this is the last, not hopefully last, but this is just a summarization of the Q learning algorithm. If you didn't kind of follow the graphical intuition and all the internal details, so you start with the Q table, okay? States cross actions, 5 cross 10, 5 cross 2, okay? Start with some state because typically every game or every situation you kind of start with some state, and then at every time step, you take an action chosen either uniformly at random with probability epsilon, which is the exploration, or with whatever is the Q value, maybe random, maybe all zeros, whichever. Take the best action that you can do for now. Okay, and so that's exploitation. And because you took that action in that state ST, you would have gotten a reward RT plus 1 and next state ST plus 1. Okay, those are the two numbers being revealed to you. RT plus 1 and ST plus 1. given those two, you can do this update, which is the same update we saw in the previous slide. Uh, Retain the previous value with 1 minus alpha weight, and add the new value with weight alpha. Okay. So this new value. So actually, this difference is called temporal difference error. Okay. So TD error, if you've heard of it, uh, that's what it's called. And also, this is called an off-policy learning algorithm. Okay. Maybe I should not off-policy learning algorithm. I will not discuss off-policy and on-policy right now, but and that's it. So this is the update, and you keep repeating it. It's a for loop. And what is epsilon? Epsilon is an exploitation parameter, just like we saw it for bandits. And alpha t is this, the moving average parameter. You can call it the learning rate in this case. And so that's it. That's the algorithm. Any questions about the Q-learning algorithm?
You might have already said this. Why do you subtract the Q, S, T, A, T at the very end there? Is it just to cancel out the first effect?
So this minus that is what? It's 1 minus alpha times Q.
Well, you still have, like, I think the learning rate coming on that would.
Yeah, 1 minus alpha t times Q plus alpha t times this thing. Okay. So this thing here is like new information about the total return. Okay. This guy is the old information about the total return. So you're just doing a moving average type of a thing where I have the old return estimate, I'm going to multiply it with 1 minus alpha, and then with alpha, I'm going to get the new return information. Is that not clear? I mean, so I should call it Q new here. It's just an update. Okay, this is an updated one. So
Sure.
it's not getting cancelled. Okay, it's like assignment here. And several years ago, okay, 92 was when somebody showed that under some assumptions, you can show that after a lot of these for loop iterations, Q is actually equal to Q star. Okay.
You say Q star just means like the optimum Q table you figured out.
Yes, the optimum Q table. Yeah. Okay. Of course, that needs some qualification because things are random here, right? So, uh, so the policy is like with epsilon probability it does something else, whereas Q star corresponds to the policy corresponding to Q star is a deterministic policy. Anyway, so this is the Q-learning algorithm. Any questions? Okay. So recap, no. So let's go here. Oops. Okay, so I did this part. Okay, so what we'll do is we'll kind of take a break, and then I'm going to talk about, and then actually the next part of this lecture is not mathematical at all. Okay, it's mostly, it's mostly because some of it is you've already seen like deep learning and stuff. So let's take a break for 8 minutes actually. At 8 p.m. we'll resume. Okay.
So is it a movie? Is it trains?
I want to quickly talk about the project. So
Yeah,
I'm using the
just one
research.
second.
So as soon as you figure out how to move the